In this video, we're going to review what we mean by a rectangular coordinate system and talk about a couple of formulas that can be applied when you're using a rectangular coordinate system. So rectangular coordinate system, Cartesian coordinate system. Perhaps you don't remember these names, but you're certainly familiar with the concept. A rectangular coordinate system is something that you've used in the past when you were labeling locations in a two-dimensional surface, what we call a plane. The way that a rectangular coordinate system works is you have two intersecting number lines, a horizontal number line that we typically call the x-axis, and a vertical number line that we typically call the y-axis. The x-axis is oriented in the normal way where the numbers get bigger and bigger as you move to the right. The y-axis is oriented so the numbers get bigger and bigger as you move up. By convention, we say that these two are intersecting at where each has reached a value of 0. So on the x-axis, the intersection point is at a component where that number line has reached 0, and same for the y-axis. We say that the coordinates of that point, therefore, are 0, 0. It has an x-coordinate of 0 and a y-coordinate of 0. And the way that we would express that is we would write those two components separated by a comma, x-coordinate first, y-coordinate second, and then we place that inside of parentheses. We call that an ordered pair, ordered because the order matters, x-coordinate first, y-coordinate second. That point is called the origin. The intersection point of the two axes is the origin. And by the way, that is the plural of axis. Not axes, but axes. We can now use these two axes to label any point in the plane. And the way that we do that is we mark the location, and then we project to each axis. Since this point sits above the x-axis, we're going to project down to the axis, find that spot on that number line, and that becomes the first coordinate of the point of the ordered pair. In this example, the point is to the right of the y-axis, so we project to the left, find what number we hit on the y-axis, and that becomes the second coordinate, what we call the y-coordinate. The two axes split the plane into 4 quadrants, we call them, and they're labeled in kind of a funny way. There's a logic to calling this one quadrant 1. Notice that the x-coordinate and the y-coordinate are both positive in the first quadrant. X is greater than 0 and y is greater than 0. So that's a logical place to start. And then for reasons that will become obvious when you get to trigonometry, if you're headed that route, we go from there in a counterclockwise fashion. So the second quadrant is to the left of quadrant 1, the third quadrant is below quadrant 2, the fourth quadrant is the only quadrant that's left over. If the point sits in a specific quadrant, then you automatically know the sign of each component of each coordinate. In the second quadrant, we're to the left of the y-axis, so x must be negative, but we're above the x-axis, so y must be positive. In the third quadrant, both x and y are negative. And in the fourth quadrant, x is positive, but y is negative. Because I know you've done this before, we're not going to go through the exercise of simply plotting points. We're going to move past that and talk about a couple of formulas that can be applied. And as we use those formulas, we'll review how to plot points as part of that. The first formula I want to talk about is called the distance formula. If you're using a rectangular coordinate system, then there's a simple formula you can apply to find the distance between the 2 points. The distance formula tells us that the distance d between the 2 points x sub 1, y sub 1, and x sub 2, y sub 2 is given by the formula d equals the square root of the sum of the squares of the differences in the x-coordinates and the differences in the y-coordinates. So you find the difference in the x-coordinates, you square that. You find the difference in the y-coordinates, you square that. You add the two together and you take the square root, and that will tell you how far apart those 2 points are. A formula like this isn't necessary when the 2 points sit on the same horizontal or vertical line. Those are easy to measure. But when you've got them at a diagonal like this, finding the distance between them can be harder to find. Here I've labeled the distance d and I've put it in red to make it stand out. And I'm going to use this picture to illustrate where the distance formula comes from. If you're like me and you have a hard time memorizing formulas, then it's often helpful to have an idea of where the formula comes from in order to get it. So again, measuring a distance on a horizontal or vertical line is easy. As a numerical example, if I'm on a horizontal axis and I've got a point sitting at 9 and a point sitting at -3, well, the distance between them is 12 because that's 9 minus -3, right? You just subtract. So we've got a more general scenario over here, but the concept is the same. I've got to find this horizontal distance here. Well, that's the difference between this x-coordinate and this x-coordinate. Now, I didn't specifically label this x-coordinate, but it's got to be at the same location on the x-axis as the point directly above it. So that x-coordinate must be x sub 2. And so that distance sitting between them is just x sub 2 minus x sub 1, and that's where that comes from in the formula. Similarly, the height of this point that I didn't label must be the same as the height of the point directly across from it, which has a y-coordinate of y1. So this vertical distance is just the difference in those two y-coordinates. That's y2 minus y1. That's where that part of the formula comes from. Where does the rest of that garbage come from? Well, you might have recognized that this is a right triangle. And so we can use the Pythagorean theorem to relate the sides to one another. A lot of people recite this as a squared plus b squared equals c squared, but you have to remember what each of those things are. So let me remind you. The Pythagorean theorem tells us that the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse, which is the longest side, the side across from the right angle. I'm going to write that in the reverse order. The square of the hypotenuse, which would be d squared, is the sum of the squares of the lengths of the legs. So I'm going to square the horizontal leg. I'm going to square the vertical leg. And now that's the square of the distance. If I want to get the distance itself, I take the square root. And some of you algebra purists might say, well, don't you have to put plus or minus? Typically you do. But here we're coming up with the distance, and we know that distances can't be negative. We've talked about that before when we were talking about absolute value. So the negative answer doesn't make sense in this application. And that's where the distance formula comes from. It's just the Pythagorean theorem in disguise. In fact, at lower levels, sometimes you just draw the picture and find the distance by labeling the sides of the triangle and using the Pythagorean theorem. But we're going to apply the distance formula. One more thing before we go. You cannot cancel these squares. A lot of times people say, well, aren't you just taking the square root of a square? If that plus sign wasn't there and it was replaced with multiplication, then yes, we could cancel those squares. But the order of operations says that we have to do this addition before we apply the square root, and so you cannot take the square root of each term. Think of it this way. If you were allowed to do that, then the distance formula wouldn't look like this. We would simplify it. But you can't. It's an order of operations issue. In this example, we're asked to find the distance between the points 3, negative 7 and 9, 1. 3, negative 7 would sit in the fourth quadrant because it has a positive x-coordinate but a negative y-coordinate. Starting at the origin, we would move 3 units to the right and then 7 units down, and that's what this lower point is. 9, 1 would sit in the first quadrant because both of its coordinates are positive. It would be 9 units to the right of the y-axis and then 1 unit above the x-axis. That's this location right here. We're looking for this distance. And the distance formula is the square root of the difference in the x-coordinate squared plus the difference in the y-coordinate squared. Because we know what the coordinates are, we can just plug the numbers in. It doesn't matter which point you consider to be x1, y1 and which point you consider to be x2, y2. Most people tend to think of the first point as x1, y1 and the second point as x2, y2. x2 minus x1 would be 9 minus 3. We're going to square that difference. y2 minus y1 would be 1 minus negative 7. We're going to square that difference. 9 minus 3 is 6, so this is 6 squared. 1 minus negative 7 is 8. That would be 8 squared. Again, you cannot take the squares off at this point and just do 6 plus 8 equals 14. That's not how the order of operations works. You'll see we won't get 14 if we follow the order of operations. The order of operations tells us that we have to square each of these numbers first, then add, take the square root of that result. So 6 squared is 36 and 8 squared is 64. 36 plus 64 is 100. And the principal square root of 100 is 10. So the distance between those 2 points is 10 units. Let me show you another example of the distance formula that just goes beyond finding the distance between two given points. This example asks us to find all points on the x-axis that are a distance 5 from the point negative 2, 4. So I've drawn the situation here. Negative 2, 4 would be in the second quadrant because its x-coordinate is negative and its y-coordinate is positive. So I've just placed it in some spot. I haven't actually measured it out. We want to find the points on the x-axis, on the horizontal axis, that are 5 units away. Now first off, how do we know that there are any points on the x-axis that are exactly 5 units away? If we go 5 units below negative 2, 4, we wind up at the point negative 2, negative 1, right? We wind up below the x-axis is what's important there. The points that are exactly 5 units away from the given point all fall on a circle of radius 5 that are centered about that point. So if we start to draw that circle, we'll see that there are 2 intersection points. We just need to figure out what those points are. Now, I intentionally didn't put any labels on the axes because I didn't want you to think that we were going to try to solve this geometrically. When you're drawing things freehand like this, that won't work. If you had graph paper and you used a compass to draw the circle, you could figure out the points. But when you're just drawing everything freehand, that won't work. We're going to do this algebraically. The distance formula tells us that the distance between 2 points can be found by subtracting the x-coordinates, squaring that difference, subtracting the y-coordinates, squaring that difference, find the sum of those squares, and then take the square root. That's the distance formula. Now, here you might object because you might say, well, we only have 1 point, so how can we use the distance formula? Well, there's one specific point given, negative 2, 4, and we'll call that one x1, y1. But there's a second point that we're searching for, the unknown point. And here's the beautiful thing, we actually know one of the coordinates of that point. We know that the point that we're looking for sits on the x-axis, which means that its y-coordinate is 0 because it's not sitting above or below the x-axis, it's on the x-axis. So while I don't know the x-coordinate, and I'm going to call that coordinate x, I do know the y-coordinate of the second point is 0, and that's going to be my x2, y2. The distance is 5, that's given. So now let's fill everything into the formula. The distance is 5, so 5 equals the square root of the sum of the squares of the difference in the x-coordinates, that would be x minus negative 2, and the difference of the y-coordinates, that would be 0 minus 4. Let's transfer this to another slide and finish off the equation here. So 5 equals, underneath the radical here, I can subtract x minus negative 2 becomes x plus 2 squared. And on the right, I get 0 minus 4 is negative 4. Negative 4 squared is 16. Do not try to take the square root of each of these terms. That does not work. We have 2 options at this point. We can either multiply out the x plus 2 by using the FOIL process, or we can square both sides. My preference would be to square both sides. I'm going to raise both sides to the second power. Let me write this as a separate step here. I would square the left side and square the right side. The left side becomes 25. The right side, the radical gets removed and we get x plus 2 squared plus 16. And I hope you can see where I was going with this. Now I can use extraction of roots. I'm going to subtract 16 from both sides. 9 equals x plus 2 squared. Now I consider cases. 9 has 2 square roots, positive 3 and negative 3. So x plus 2 equals 3, or x plus 2 equals negative 3. Solving each equation, we get that the x-coordinate could be 1 or negative 5. Remember that the y-coordinate of the point was 0 because it's on the axis. So the 2 points that we're looking for are 1, 0 and negative 5, 0. In our picture here, which isn't perfect, this point is 1, 0 and this point is negative 5, 0. We'll use the distance formula one more time later on in this video, and it'll be closer to what we did the first time with it, but it'll still be with a purpose, with an application. Before we talk about that, let me talk about another formula that we can apply when we're using a rectangular coordinate system, and that's the midpoint formula. The midpoint of a line segment is the point that's halfway between the endpoints. It's a pretty straightforward name. There's a simple formula you can apply when you're working in a rectangular coordinate system and you know the coordinates of the endpoints. The midpoint of the line segment with endpoints x sub 1, y sub 1, and x sub 2, y sub 2 is found by taking the average of the x-coordinates, so you add the 2 x-coordinates together and divide by 2, and then you average the y-coordinate, y1 plus y2 divided by 2. There's kind of a logic to it. If you're trying to find the point halfway between 2 points, we'll call it m for midpoint. Well, you're trying to find the distance halfway across this horizontal line segment. Well, that's going to be dead smack in the middle here, and that's just going to be the average of those 2 x-coordinates. Same logic here. We want to find this location halfway up this vertical line segment, well, it's going to be average of the two y coordinates, y1 and y2. So the midpoint has an x coordinate of x sub 1 plus x sub 2 divided by 2, just the average of the x coordinates. And similarly, the y coordinate of the midpoint is y sub 1 plus y sub 2 divided by 2. Here's a simple example of that. We're going to find the midpoint of the line segment with endpoints negative 6, 7 and 2, 3. Negative 6, 7 is in the second quadrant because it's got a negative x coordinate and a positive y coordinate. 2, 3 would be in the first quadrant because both of the coordinates are positive. Let's see what the formula says. The formula says that the midpoint is found by taking the sum of the x coordinates and dividing by 2. That's your x coordinate of your midpoint. And then take the sum of your y coordinates and divide by 2, and that will be the y coordinate of your midpoint. So we'll do the standard labeling where the first point we were given is x1, y1, and the second point we were given was x2, y2. Let's find this midpoint. So that'd be negative 6 plus 2 all divided by 2, and then 7 plus 3 all divided by 2. This arithmetic isn't difficult, but a lot of people will still use their calculators, especially on exams, which I encourage. You shouldn't risk losing points just out of mathematical pride. It's okay to use your calculator even when the arithmetic is easy. If you're going to do this arithmetic in the calculator, make sure you do the addition first and then divide, or use parentheses. Don't type something like this. The calculator is strict about the order of operations, and it's going to do the division first and then do the addition. If you want to make sure the addition happens first, slap parentheses around it. A lot of students, when they're learning the order of operations, will complain and say, why do I have to learn this? I have a calculator. That's exactly why you have to learn the order of operations, because your calculator is going to follow the order of operations, so you have to know the order of operations in order to use it. We're going to do the addition first and then divide. So negative 6 plus 2 is negative 4 divided by 2, and that's 10 divided by 2. And so now we divide and we get negative 2, 5. It's going to be somewhere about here at negative 2, 5. Now, if you're nitpicking me and saying, well, that doesn't look like it's really in the middle, that's because my drawing is bad, not because the math is wrong. If we were doing this on graph paper and using rulers and such, you could verify that that was the midpoint. Simple idea. Let's apply both the midpoint formula and the distance formula to another type of example. This says the diameter of a circle has endpoints negative 3, negative 7, and 2, 5. Find the center of the circle and the length of its radius. So I've drawn a picture of the scenario on the next slide. The thing I drew doesn't look like a circle, I know, just shut up. Pretend that egg is a circle. I've plotted the 2 points we were given. Negative 3, negative 7 would be in the third quadrant because both of its coordinates are negative. So this is the point negative 3, negative 7 down here. Let me label it. The other point we were given was 2, 5. That would be in the first quadrant. Let me label it as well. We've been asked to find the center of this circle and the radius of this circle. And in order to do that, you're going to have to remember what that means. The center of a circle is actually not a point on the circle. It's the point equidistant from every point on the circle. So you can imagine it's going to be somewhere in here. It's hard to tell because I drew an egg, an oval, not a circle. But there's some point here that's equidistant from every point. Now, how are we going to find that center? Well, there was another math term here, and it's important. We were told that those points were the endpoints of a diameter of the circle. A diameter of a circle is a line segment that goes through the center of the circle. So if it goes through the center of the circle, the center's got to be sitting in here, and that's going to be the midpoint of that diameter. The midpoint of a diameter is the center. So how do we find the center? Well, we'll apply the midpoint formula. We're going to add the x coordinates, divide by 2. We're going to add the y coordinates, divide by 2. Negative 3 plus 2 is negative 1, divided by 2 is negative 1/2. Negative 7 plus 5 is negative 2. Negative 2 divided by 2 is negative 1. Now we need to find the length of the radius. So what is a radius? Well, the radius is the distance from the center to any point on the circle. So in particular, we could find the distance from the center to this point in the first quadrant. Alternatively, we could find the length of the diameter and then divide it by 2, and that's what I'm going to recommend in this example. Both are good strategies, But the nice thing about finding the diameter is that I get to use integers. If we use the center, we've got this silly fraction that we have to deal with, and that's not the worst thing in the world, but if we can avoid it, it would be nice. So I'm going to specify that I'm finding the diameter first. So we're going to take the square root of the sum of the squares of the differences in the x-coordinates and the y-coordinates. I didn't label these for the midpoint formula, but let me put these labels on here. x1, y1, x2, y2. The difference in the x-coordinates would be 2 minus negative 3. The difference in the y-coordinates would be 5 minus negative 7. 2 minus negative 3 is 5. 5 squared is 25. 5 minus negative 7 is 12. 12 squared is 144. That's the square root of 169, which is 13. The radius is going to be half of that, so it's 13 over 2, or 6.5. You can do this by just measuring the distance from the center to either point. I will put that on the next slide, but I'm not going to make you watch me do the math. But here it is. So I've demonstrated this with the center and the point in the first quadrant. We could also do this with the center and the point in the third quadrant. The distance will be the same because the radius is the same from the center to any point. That's what makes a circle a circle. I think that's sufficient practice over these, especially since most of you have probably seen this before. If there's anything in this video that doesn't make sense or that you'd like clarified, just let me know. Shoot me an email, see me in an office hour.